Bismillahirrahmanirrahim. So here we have a problem. Uh, Consider a two-dimensional random vector x bar with the PDF given below. So fx x bar uh, is equal to 2, while x1 is greater than or equal to 0, less than or equal to x2, and x2 is less than or equal to 1, and this is 0 otherwise. And this bar here denotes that this is the PDF of a random vector, right? Find the following: expected value of the random vector, correlation matrix, and the covariance matrix. So let us first notice that the variables here, the random variables here are x1 and x2. We are given that this is a two-dimensional random vector. So this random vector, it comprises of two elements. So we can say that x bar is equal to x1 and x2, right? So this is a two-element random vector. And let's also plot this region of where this PDF is non-zero. So we have, let's take x1 along the horizontal axis and x2 along the vertical axis, right? So the significant line here is x1 equal to x2. So that is this line here. x1 is equal to x2 at this line. So it's given that x1 is less than or equal to x2, right? And x2 is greater than or equal to x1. So let's assume a point here for sample. So if you notice the coordinates of this point, right? So x2 is less than this coordinate x, the value of this x1 coordinate here, right? So it is not this region that we are interested in. So x2 must be greater than x1. So similarly, suppose a point here. If you take a point here, the value of x2 coordinate is greater than this x1 coordinate, right? So this satisfies this this constraint here. So x2 greater than x1 is this region, right? And x1 is greater than 0. It means we are on the right side of this axis x2, right? And x2 is less than 1. Suppose we have a 1 here, x2 is a 1 here. So x2 is equal to 1 is this line, right? Is bounded by this line. So x2 is less than or equal to x1, is below this, and x2 is greater than x1 is this region, right? So it is basically this region where this probability is non-zero, right? So and the coordinates of this point, this is this x2 is 1 here, right? And this line is x2 is equal to x1. So as x1 is equal to x2 and x2 is 1, so x1 is also 1 here, right? So the coordinates of this point are 1, 1. This is the origin, 0. So now the expected value of the random vector x. So as we know that x is a column vector comprising of two elements, so expected value of x is given by this column vector where each entry is expected value of the corresponding random variable. So it means that we need to find out the expected value of x1 and expected value of x2. One way to do that will be to derive the marginal PDF of x1 and marginal PDF of x2. For example, marginal PDF of x1 is given by fx1 x1 is equal to minus infinity to plus infinity fx x. This is the PDF of the random vector, right? And we need to integrate out the variable x2 from this joint PDF, the vector PDF, right? So in our case, the limits for x2 will be from x2 is equal to x1 here to x2 is equal to 1 here. So x2 is equal to x1 to 1, and the value of the PDF is 2, and we integrate with respect to x2. So with this integral we can get the marginal PDF of x1. Similarly, marginal PDF of x2, this was the marginal PDF x1, marginal of PDF x2. This can also be obtained. fx2 x2 is given by 2 dx1, and we are integrating with respect to x1 now. So the limits of x1 will be from 0 to x2, 0 to x2. So with this integral we can get the PDF of x2. So using these marginal PDFs, we will be able to derive the expected value of x1 and expected value of x2. However, we can derive the expected value directly from the PDF of the random vector also. So let's do that. So alternatively, expected value of x1, for example, is given by this double integral, minus infinity to plus infinity, minus infinity to plus infinity here. So this will be x1, so fx x bar and dx1 dx2 here, right? So expected value of x1 is given by x1 multiplied by this PDF of the random vector, which is 2. So 2 is a constant, we can write it outside here, and we are left with x1, and we need to integrate with respect to x1 and with respect to x2. So this will be the limit for x1 and this will be the limit for x2 here, which can be found from this region here. So let's assume a strip this way here. So x1 is from 0 to x2 here. x1 is equal to, right? This is this line, x1 is equal to x2. So x1 will be equal to x2 here. So x1 is equal to 0 to x2, right? And x2 is from 0 to 1. So when we integrate with respect to x1 now, so this will be x1 square over 2. So 2 over 2, we can take it outside, right? And x2 is from 0 to 1. This will be x1 square over 2. We have taken 2 over 2 outside, 1 over 2 here, right? And the limits are for x1 are 0 to x2, and we still need to integrate with respect to x2 here, right? So now expected value of x1 is given by, this cancels out, and x2 is from 0 to 1, and let's put in the limits now. So this will be x2 square, right? So x2 squared and dx2 here. So this will be 1 over 3 x2 cube 0 to 1. So this will be 1 over 3 into 1 minus 0. So expected value of x1 is basically 1 over 3, right? So this gives us the expected value of x1. So let's now find out the expected value of x2. So expected value of x2, it can also be found using the marginal PDF of x2, but or we could find the expected value also using the PDF of the random vector as well, like we did for the expected value of x1. So this is given by this integral, minus infinity to plus infinity here, minus infinity to plus infinity, right? x2 fx x and dx1 dx2, right? So this is this double integral here. So fx x bar, this is 2, right? So 2 is a constant, it can be written outside here, 2, and x2 dx1 dx2, this should be the limits of x1, this should be the limits of x2. So the limits for x1 are again from 0 to x2, right? x1 is equal to x2 here at this line, right? So x1 is equal to x2. So x1 is equal to 0 to x2, and x2 is from 0 to 1. x2 is from 0 to 1 here. So this will be 2, and x2 is equal to 0 to 1, and this will be x2 square over 2. So 1 over 2, let's take it outside here. So this will be x2 square, right? And the limits will be sorry, we are integrating first with respect to x1, right? So x2 is a constant with respect to x1, so this will be simply x1 here, right? So this will be x1 here without any square. So x2 will be still multiplied with multiplied by this x1, this result, right? So limit for x1 will be from 0 to x2, and we still need to integrate with respect to dx2. Let me repeat here. We are integrating first with respect to x1. So x2 is a constant with respect to x1. So this will remain outside here, and integral with respect to x1 will result in simply x1 here, right? No 1 over 2 here also, right? So this will be x1 here, and the limits will be from 0 to x2, and we still need to integrate with respect to x2. So this will be 2 here, x2 is equal to 0 to 1, and when we put in the value of the limit, this will become x2 minus 0, and simply x2, right? x2 multiplied by x2 will be x2 square here, x2 square, and dx2 here. And further integration will result in 2 into x2 cube over 3. So over 3 can be written here like this. So this will be x2 cube, limits 0 to 1. So this will be 1. When we put in the limit, this will be simply 1, right? So this will be 2 over 3 minus 0, right? So the expected value of x2 is simply equal to 2 over 3, right? So we have determined the expected value of the random vector now. So expected value of random vector x is given by expected value of x1 was found out to be 1 over 3, and expected value of x2 is 2 over 3. So it is this vector, expected value of the random vector x. So we are left with part B and C. We need to find out the correlation matrix Rx. Part B is correlation matrix Rx, right? So the correlation matrix Rx is given by this expectation, expected value of x bar multiplied by x dash bar. X dash means transpose of x, right? So x is x dash bar is basically x1 x2, this row vector here. So x bar x dash bar will be equal to x1 x2, this column vector multiplied by this row vector here, and this will result in x1 square here, x1 x2 here, x2 x1 here, and x2 square here, right? And their expectation is a linear operation, right? So x bar x dash bar, which is basically the correlation, is given by expectation of x1 square, expectation of x1 x2, expectation of x2 x1, and expectation of x2 square here. So we need to determine this matrix now. So again, expected value of x1 square and expected value of x2 square could be determined using the marginal PDF, or it could be determined using the PDF of the random vector. So let us do this later option. So expected value of x1 square is given by this integral minus infinity to plus infinity, minus infinity to plus infinity here. So x1 square multiplied by the PDF of the random vector and integral with respect to dx1 dx2 here, right? So let's put in the values. So this is given by x1 square. So fx of x is, as we know, is 2, right? So 2 is a constant, it could be written outside here. So this is x1 square here, and 2 is already here, dx1 and dx2. Limits for, we are integrating first with respect to x1. So limit for x1 are again from 0 to x2, 0 to x2, and limits for x2 are from 0 to 1, right? So this is 2 constant here, 0 to 1, which are the limits for x2, right? And if we integrate it with respect to x1 first, so this will be x1 cube over 3. So 1 over 3 can be written here. So this will be x1 cube, right? And the limits for x1 are 0 to x2, 0 to x2, and we still need to integrate with respect to x2. So this will be 2 over 3, right? 0 to 1, and we put in the limits. So this will be x2 cube. So x2 cube and dx2 here. And if we integrate it, we will get x2 raised to the power 4 over 4. So 2 over 3 into 4, and we have x2 raised to the power 4 here, and the limits are from 0 to 1. So this will be this will cancel with this 1 over, this will become 2 here, so 1 over 6 into 1 minus 0, so this is 1 over 6 here, right? So expected value of x1 square is 1 over 6. This is the first entry of this correlation matrix, right? So let us find this expected value of x2 square also. So the expected value of x2 square is given by this double integral. Again, we can write the value of the PDF, which is a constant here, 2, and then x2 here, x2 square here, right? We are calculating the expected value of x2 square, right? So x2 square and dx1 dx2, and the limits for x1 and the limits for x2 here. Limits for x1 are 0 to x2, and limits for x1 are 0 to x2, and for x2 are 0 to 1. x2 are 0 to 1. So this 2 is a constant and x2 is 0 to 1. So we are integrating first with respect to x1. So x2 square remains the same. So we get x1 here with limits 0 to x2 and a dx2 here. So this will become 2, 0 to 1, this limits. So this will be x2. So x2 multiplied by x2 square will be x2 cube, right? And a dx2 here. And when we integrate, so this will be x2 raised to the power 4 over 4. x2 raised to the power 4 with limits 0 to 1. So this will result in 2 over 4, right? Or 1 over 2 into 1 minus 0, which is 1 over 2. So expected value of x2 square is 1 over 2. So we have determined this entry and this element also of the correlation matrix. We are left with this expectation of x1, x2 and expected value of x2, x1. This is basically this element is the correlation of x1, x2, the random variables x1, x2, right? So let us find next the expected value of x1, x2, which is given by this double integral minus infinity to plus infinity here, minus infinity to plus infinity, and x1, x2, fx of x, dx1, dx2, right? And this is given by the PDF is a constant 2, right? This will be the limits for x1, this will be the limits for x2, and we have x1, x2 here. We are integrating with respect to x1 and x2. The limits for x1 are again from 0 to x2, 0 to x2, and the limits for x2 are 0 to 1, right? And now we are integrating first with respect to x1, right? So this is x2 is equal to 0 to 1. So this will be x1 square over 2. So this 2 already here, and we get 1 over 2 here, right? So this will be x1 square and with limits 0 to x2, and we already have an x2 here, and we still need to integrate with respect to x2. So this will be, this cancels out. So this will be 0 to 1, x2 is equal to 0 to 1. So this will be x2 square when we put in the limits. So this x1 square will come out to be x2 square multiplied by x2. So that will be x2 cube and x2 here, right? dx2, right? So this will be basically x2 raised to the power 4 over 4. So 1 over 4 x2 raised to the power 4, x2 raised to the power 4 with limits 0 to 1. So that will be 1 over 4 into 1 minus 0, so that is 1 over 4 here. So expected value of x1, x2 is 1 over 4, right? Now we have determined this entry here. We left with this one only. So expected value of x2, x1 is basically is the same as this one because as you see this is equal to this integral. So 2x2 x1 and dx1 dx2 here with limits x1 is equal to 0 to x2 and x2 is equal to 0 to 1 here, right? So the order of multiplication does not change the result here, right? So this is essentially equal to expected value of x2 x1 is equal to expected value of x1, x2 is equal to 1 over 4, right? So the correlation matrix of the random variable x is given by, let's put in the results now. Expected value of x1 square was 1 over 6, right? So this is 1 over 6 here. Then expected value of x1, x2 is 1 over 4. That of expected value of x2, x1 is also 1 over 4. And expected value of x2 square is 1 over 2. So this is 1 over 2 here. So this gives us the correlation matrix of random variable x. So we're done with part B of the problem also. So part C is the covariance matrix. Covariance matrix, right? So the covariance matrix of random variable x is given by this expression, is equal to the difference between the correlation matrix minus mu x and mu x dash bar. And this is the expected value of x, right? So we have already found this correlation matrix. We just need to determine this product here and then subtract it from the correlation matrix to get the covariance matrix. So mu x we have already found, which is the expected value of x, is given by, we found that out earlier, is given by this column vector 1 over 3 and 2 over 3. 1 over 3 and 2 over 3 here. So mu x dash, that is the transpose of this one, which is x dash bar, is equal to 1 over 3, 2 over 3. This is a row vector, right? So we can easily calculate this product then. So mu x bar, mu x dash bar is given by this product 1 over 3, 2 over 3, this column vector multiplied by this row vector 1 over 3, 2 over 3 here. So when we multiply it, we get 1 over 9, right? And then 2 over 9 again here, 2 over 9 here, and that is 4 over 9 here, right? So we need to subtract this matrix from this one according to this formula. So Cx is given by, let me write down the matrices, is 1 over 6, 1 over 4, 1 over 4, 1 over 2, minus 1 over 9, 2 over 9, 2 over 9 here, 4 over 9 here, right? So this should be equal to 1 over 6 minus 1 over 9, right? So 1 over 4 minus 2 over 9, and again 1 over 4 minus 2 over 9, and 1 over 2 minus 4 over 9. So this is simply arithmetic now. So 1 over 6 minus 1 over 9, the LCM is 18, right? So this is 3 minus 2, which is 1 over 18, right? So this entry will be 1 over 18, and 1 over 4 minus 2 over 9, the LCM being again 18, right? So this will be, no, the LCM will be 36, sorry, this time LCM is 36. So this is 9 here, 4 into 9, 36, and this is 9 into 4, 36, 4 into 8. So this will be 1 over 36. So this entry is the same as this one, and we are left with 1 over 2 minus 4 over 9. 1 over 2 minus 4 over 9. So LCM again is 18 here. So this is 2 into 9, 18, minus 9 into 18, 2 into 4, 8. So that is 1 over 18. So we can write down the covariance matrix. So the covariance matrix is given by, now 1 over 6 minus 1 over 9 was found out to be 1 over 18, right? So this is 1 over 18 here, the first entry. The second entry, 1 over 4 minus 2 over 9, this was found out to be 1 over 36. So 1 over 36 here. And next, this is similar to this one, again 1 over 36. And the last entry, 1 over 2 minus 4 over 9, was 1 over 18. So this is 1 over 18 here, right? So this is the covariation matrix. So we also know that for two element random vector, the diagonal entries are variances. This is variance of x1, and this is covariance of the second entry is of x1, x2, and this is the covariance of x2 comma x1, and this is the variance of x2 here. So comparing this result with this matrix here, so we can also see that variance of x1 is 1 over 18, and variance of x2 is also 1 over 18, right? And covariance of x1 comma x2 is equal to covariance of x2 comma x1 is equal to 1 over 36. So this concludes the solution to this problem.